at this motor we need to design. So you have a requirement where you need to design a 2 Newton-meter motor, and it needs to produce a torque of the 2 Newton-meters of the 2050 RPM. And then you have the field weakening capability of the 6,000 RPM, right? So this is your requirement. Okay, so base speed is 2,750 RPM, and then you want to have a 0.92 Newton-meter torque at 7 RPM. Your power is 575 watts. Voltage is 24 volt DC. Controller current 30 amps RMS continuous, and then with 40 amps RMS speed 15 seconds. And then your motor diameter is 90 millimeter max, and motor length is 110 millimeters. So these are the requirements you get from a customer saying, okay, I want you to design a system for us with these specifications. Now, so you do some math. You say, okay, if I have a 90 millimeter motor diameter, then I can set my stator, because stator also has to have a housing. So I can set the stator at 83 millimeters, and rotor diameter I can decide between 0.4 to 0.6 ratio. That means I can have between 33.2 millimeter, 49.8 millimeters. So we want to have an optimum design, max torque, and those are the requirements. Basically, we did a simple math, and so that's our options. Stator diameter 83 millimeter. Rotor diameter can be anywhere from 33.2 millimeter to 49.8 millimeters. Now we further convert that. So for a 70 millimeter stack, we'd say that your torque per unit rotor volume, this is your range in which you need to be. This is your lower range, 2 Newton-meter at 70 millimeter stack. Because you are limited to the length of the motor. So we determined that max stack we can have is 70 millimeters. And then you're at 2.5 Newton-meter, if you target 2.5 Newton-meter, you're going to have this kind of torque per unit rotor volume, depending on the motor diameter, where you end up being rotor diameter. And we do some calculations here, torque per unit volume. We look at for 33.2 millimeter rotor diameter, your torque per unit rotor volume is going to be 2 by this formula, pi r square. And the 70 millimeter stack, it's going to come down to 33 kilonewton-meter per meter cube. Okay. For 49.8 millimeter diameter, it's going to be 14.67 kilonewton-meter per meter cube. So we're going to have a pretty high torque density here compared to this motor. Okay, so let's see where we end up. So this is one of the torque equations you can use to roughly estimate your electromagnetic torque. You can say, okay, 3 by 2 dl B. So D is your air gap diameter, inner stator diameter, or bore diameter. L is your stack length. Then you can say, okay, this is my operating magnet density in Tesla. This is my magnet arc angle in electrical degrees, beta. This is NS is my number of turns per phase. IM is the peak phase current. And then you have a delta is a control angle between magnet flux and stator current, which normally would be 90 degrees below the base speed. Okay, so you can roughly use this equation to estimate your electromagnetic torque. And so here is what we do. We say, okay, we want a diameter of 45 millimeter, length of 70 millimeter. We want 1 Tesla flux density, beta of 90 degrees, number of turns turning once, 56 amps, delta is 90 degrees. So it gives us electromagnetic torque of 55 tons of okay. Roughly using that formula. That's where it comes out to. So here is, you plot that equation with respect to your diameter. It's a linear equation in this case, and it varies from 4 Newton meter to 6 Newton. So this is how you can say, okay, this is the size given by the customer. This is going to be my range of the torque. I have not decided number of holes. I haven't decided the architecture inside, but this is going to hold true based on just the general dimensions of the lumen. So what we do is we take this information and then we say, okay, how many different architectures we can consider? So we can consider rotor architectures, surface mount magnets, IPM motor with lateral magnets, IPM motor with angled barriers, IPM motor with V magnets, or IPM motor with spool magnets, right? So these are on the table for us to see what we can do. So these are the different pole slot configurations we went through. 6 pole, 9 slots, these are the stator slots, these are the magnet poles. So you can see how we came across, so, okay, these are all the things on the table, IPM, SPM, between IPM and SPM is what we consider as different architectures when we consider slot pole architectures. So here is the surface mount. The first motor we want to discuss is you have the stator here, you have the magnets here, and you have the rotor, right? So the tooth width here is 6 millimeters here, okay? So we're going to do the first comparison between SPM motor, and this one is 11.6 millimeter. You can see here, we are trying to see what happens if you were to increase your tooth width. So there are 2 designs on the table. We have a stator diameter of 83 millimeters, rotor diameter is 46 millimeters, air gap of 1 millimeter. Magnet angle is 30 degrees. Magnet thickness is about 3.5. Phase resistance, you can see, is for design A is 0.03095 because we have taken away the copper and we have given the copper to lamination because lamination will take more room. So your tooth width is 11.6 millimeter here, and your everything else is about the same. Your stator core, obviously, you increase your lamination by 0.25 approximately kilograms, and your stator winding mass has gone down here, whereas with a 6 millimeter tooth width, you had a more copper here. We use a neodymium iron boron 4023 magnet, and we have a lamination material of N19. Okay, that's the kind of design we start with. We basically draw a line in the sand, and we say, let's start with one design and see how it progresses. So here you can see we plotted torque versus rotor angle. And the red one is the one with the 6 millimeter. And then this one, 11.6 millimeter, is with the 11.6 millimeter, the top one with the tooth width, right? So you see here, our torque estimation was pretty close, 5.6 Newton meters. And you can see this one is coming at about 4.8 Newton meters, and this one is coming about 5.3, 5.2 Newton meters, right? So you have 10%, there's a reduction of 10% in torque, while the resistance has been reduced by 46%, right? So comparing between 11.6 to 6 millimeter, we reduced the torque by 10%, but the resistance has been reduced by almost half, okay? So that means it gives you more efficiency in terms of the design. So here is a torque speed curve. It does not meet our requirement of 2,750. Customer only wants 2 Newton meters. So we know we have a lot of room in the motor, right? We are already producing 5 Newton meter torque. So we know we have a lot of room, but we are not able to hit the speed. We need the speed to be 2,750 RPM at 2 Newton meters. So this guy has to go all the way up to close to 3,000 RPM. So these designs don't hit it. All the way getting a good amount of power here up to 2,000 RPM. You can see green is the power here, and these are the two torque speed curves. So we're getting a good amount of power, close to 900 watts or so, but it does not meet the customer specifications. So here is with phase advance. If you implement field weakening, you reduce this is a constant field weakening, so you're able to reduce your torque for both designs, but you're extending your speed range with this one. And the result is that you are actually getting close to, still, I guess I'm cut out here for some reason. So we'll see what that is. Somehow this is cut out. Yeah, here is the better picture here. So your this one, so you have a 6 millimeter teeth design here, which goes like that, and you have 11.6 with a plus. That is your power, and then your max torque. The dots are the 11.6 millimeter are the dots. Okay, so 3,000 RPM, we are achieving 3 Newton meters here. Like in both the cases, we can achieve 3 Newton meters here. So this design could meet the customer requirements quite well. And 2 Newton meter, we can have up to 4,000 RPM. So possibly with your phase advance, you can get there. Okay. Now let's look at some of the plots, flux and flux density distribution. So this is your 45-degree rotor position, 56 amps of peak current you're pushing. That means you divide 56 by 1.414. That'll give you the RMS current. So you see here this is all SPM magnets, and you can see that your flux density is going up to 2.1 Tesla. So you have some areas of concern here, here, here. And you can see your lines of flux are pretty uniform all around. But that's the good news. There is not a whole lot of, so we see healthy lines of flux. We see some saturation here in these legs here, and because we're pushing a pretty high current, 56 amps current. So now when you look at the stator back iron, what is stator back iron? Stator back iron is you're looking at the flux here. This is the circle here, which is the stator back iron. Okay. So stator back iron is a good indication of harmonics, what kind of harmonics you may experience in your torque. So if you see here, this stator back iron starting from
So are
0
you
degrees.
sharing your screen? I am not able to see.
Is everybody able to see
It's
my screen?
Yeah, I can see your screen.
Oh, then it's my. I'll just reconnect then.
I can try sharing my screen again. Let me try that. Let me stop the sharing, and then I will start sharing my screen again. Okay. See if that helps. Okay, so here you're looking at your stator back iron from 0 degrees to 360 degrees. So we see the flux density goes from about 0.1 Tesla all the way up to 1 Tesla. So not too bad. That's healthy. And this is where you have got some discontinuities here, right? So these discontinuities can lead to higher order harmonics in producing the back EMF. Right. So basically, our target is every time our target is having a perfect back EMF in the air gap. Okay. So as you're pushing a higher current, you're going to see some discontinuities happening all around. The discontinuities are happening simply because you have got these effects happening here. Okay. Saturation is going to lead harmonics into your more performance. Some of them are avoidable, some of them are not avoidable. based on how much performance and how much optimization you need. So now let's look at tooth width. So now what we're going to do is we go in here and look at the tooth. This black circle will shrink down and look at the tooth width. What's happening in the tooth width? So if you look at the tooth width, you can see here that there is flux all the way approaching up to 2 Tesla here. And this is where you are. You do want to push your lamination to a lot of flux, but you want to avoid saturation, right? Because once you saturate, then you introduce a lot of issues in terms of harmonics, in terms of back EMF not being sinusoidal, and then introducing more ripple in your design. So you can see here the where you have higher flux, that's where you have also the points of a more discontinuity, right? Here it's very smooth and continuous, but then here is where it starts becoming discontinuous. Okay, so that aligns with that, and then let's look at your tooth tang. So tooth tang is the area of the flux, area of the stator. These are all tooth tangs, right? Tooth tang is close to the air gap and close to the magnets, close to the rotor, right? So this is where the action is happening, where the transfer of power is happening between the rotor and the stator. So tooth tang is an important part. So we look at the tooth tang and you can see that tooth tang 0 to 360 degrees again, you're approaching 2 Tesla here on this part, right? So you can basically measure, you have, this is a 9, you should have 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. So we have got 1, 2, 3, 4, 5, 6, 7, 8, 9 peaks. So the 9 peaks here, and you have at least 2 of these approaching 2 Tesla. So that can be an area of concern. That's your tooth tang, how they're responding, right? And then you look at your air gap, what's happening in the air gap. So in the air gap, you have peaking phenomena happening here. At you can see here 60 degrees. You have basically 1, 2, 3, 4, 5, 6, 7, 8. And you're missing 1, 2. Yes, so we have 8. Okay, so this is a reaction because of the magnets, because we have 8 magnets here. So you have, so this air gap flux density distribution is going to tell me that I'm not going to have a perfectly sinusoidal distribution. And these discontinuities will lead to some kind of a vibration or space harmonics, right? Okay, so, and then you look at the flux lines here, what you see is flux density distribution in the air gap. This is your circle, which will tell you what is your flux density distribution in the air gap. So the flux density peaks when the next tooth is encountered at 62.3 degrees. That's what you see here, 62.3 degrees, right? This is where you have this peak happening. And this is happening because you are interacting. So this is where peaks when the next tooth is encountered at 62.3 degrees. That's your stator tooth you're encountering. And the flux density drops at the end of the teeth 59 degrees. That may be difficult to see here, but that is your interaction happening between a magnet and the stator, and that's resulting in the peaking of the air gap flux density. Okay, so now let's look at what's happening at the magnet level, right? So you have a north magnet and the south magnet, and we have 8 magnets. So let's see, 1, 2, 3, 4, 5, 6, 7, 8 magnets, right? So, and you can see here that because of normally you're supposed to have a uniform magnetization. But now the magnetization is no longer uniform. You have interesting flux density pattern between various magnets, right? You're a north pole, the north pole and the south pole. So you can see one is you don't really have equal flux density between them. And then you have these discontinuities which happen in the magnets, right? And then let's look at the center of the magnets. Center of the magnets are a little better, but you still have a known uniform flux density distribution in the magnets. Okay. And then rotor back iron. Rotor back iron is basically, let's see if we can go back to the picture. So rotor back iron is going to be something somewhere here. Okay. So it is away from the magnet, it's away from the action, but you can still see variation of the flux in the rotor back iron. Right. So it's a pretty good variation from almost 0.82 to 1.3, let's say. Right. So you have a pretty good 0.5, that's the relation. And you have a frequency here. So you 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it's basically double your magnet number of magnets. Okay, so caulking torque. So caulking torque between the 6 millimeter, which is the red one, is pretty small, 0.015 meter, and the blue one is 11.6 meters. The caulking torque looks fairly significant here, looks at nature. And this is your line and back EMF. Now, line and back EMF. Now, this is again without any current. You have to remember the waveform looks very nice. You can still see some distortion, not perfectly sinusoidal, but this is at zero current, your back EMF. That's how it looks like. You have a line and phase back EMF. This is your line and flux linkage here. This is with respect to the position down here. Some of the x-axis, but that's what you have, the line and flux linkage. Basically, your line and flux, a line and neutral. This is going to give you your LD and LQ values. This is your air gap flux. Weber, essentially. So this is your flux, shaping of the flux in the air gap. I think we have taken only one so this is over just one electrical pole. Again, this one is without any excitation. Just one is electrical release here. You start from somewhere middle of the north pole. Air gap flux density at zero current. So you can see here you have some discontinuities here, even at zero current. Okay. So you can see your air gap flux density varying here from -1 S-lot. That's what's happening when there's no excitation. So that's a kind of variation you have. But here your north pole and south pole are also right. There are 4 north poles and those. They're all equal in your nice transition between the south pole. And this here is your 56 amps, the radial flux density. This was your zero current, the radial flux density. I guess we have radial flux density is not too bad in terms of your reaction to the current. Okay, so Let's look at one more design, IPM with lateral magnets. Here you have internal magnets here embedded in the rotor. And here we change. So this design here, I guess IPM electromagnets produces less for 3 newton-meter for compared to the 6 millimeter surface mount magnet. And so that comes out to, or this. I think we're done with the spoke magnets. So that will, all right, spoke magnets. So this is how you have another design with spoke magnets, where you have removed your surface mount magnets and replaced them with spoke magnets. And the spoke magnets, if you apply, I think they're misplaced here. Okay, so we're going to compare 3 designs of spoke magnets. And we are going to have an air gap thickness of 0.5 millimeters, stator diameter of 83 millimeters, stack length of 70 millimeter, number of holes will remain at 8, number of slots will be 9, rotor diameter is going to be 42, 43, and 46 here, and then inner diameter is going to be 18, 18, based on our shaft requirements. And here we are going to have a different in slot area. For design B, we're going to have 117 millimeter squared, 236. This is 5. This is 5.25. This is a tooth thing, the 2.25, 3, 1.05. Tooth gap width 1.5, 2.5, 2.5. And the back end depth of 9, 8.5, and 7. Okay, and the number of turns is 8. So here is your design A. We are looking at flux distribution at 0 speed. So you basically have got negative Webers to positive Webers, minus 3.07 microwebers to plus 3.07 microwebers, right? So this is per millimeter. So you can see here, red is essentially your north polarization, and then the blue is your south polarization, and you have these shades of colors in between. Okay, and here you're looking at, these are your magnets here. Yeah, 4, 1, 2, 3, 4 south magnets, and then 1, 2, 3, 4 north magnets. That's your flux distribution inside your motor. And here is your flux of the air gap, which looks so beautiful, perfect, right? This is the kind of flux you would like to see, where it's perfectly sinusoidal, and you got 4 peaks and 4 valleys. Okay? And here is your flux density distribution here, and the flux density distribution here at 0 current looks very nice. You are pretty much in the up to the green zone, where you don't get into yellow or orange or red zone. So that looks very nice. So let's look at the flux density. I don't know whether this is it. Where this flux density is. This is. Let me see if I can. Okay, so there is distortion of the flux Weber per millimeter when you start pushing the current. So you can see our nice, beautiful sinusoidal waveform has been distorted with the when you start pushing the current in it. So this is your flux distribution when you push current into the motor. Okay, and now you're going to minus 5 microwebers to 4.62 microwebers per millimeter. Okay, and this is your air gap circle here, right here, which you are looking at. with the 56 amps of current. And this is your phase and line back EMF voltages. Here you can see some distortions here, not really perfectly sinusoidal as we would like to have. And then let's look at air gap flux density, 56 amps of current. You can see we still don't have any saturation, which is nice, right? Here we're going up to yellow points here. But I guess that is close to 3.19 Tesla. You have a larger scale here. So most of the design seems to be in this blue region. And this is your air gap flux density, where you can see you have quite a bit of discontinuities here. And you have peaking here, but nothing is and average torque is kind of reduced compared to the other design in the torque in the motor. So you look at the average torque, you can see there is a ripple in average torque. So all of that back EMF, all of those flux discontinuities are going to result into your ripple. Okay. You can only do so much in your controls. If your back EMF has got harmonics, you're eventually going to see those in your torque. So you have a design A and design B. The ripple seems to be pretty similar, and just design B is producing a little bit of more torque. So this is your fogging torque, still about the same as we had seen before, 0.015 millimeter. Design B back NF, we still see some distortions here, another ideal waveforms. And this is your flux distribution again, zero stator current. This may be a different design. They look pretty sinusoidal. Okay, and then design C. So this is your design C here. Design C, this is with the current, so you can see the current begins to distort their gap flux quite a bit. And flux and radial density plots, you have here going up to 2.1 Tesla. You have the line of flux. I am worried about the much less torque here, much less flux lines here. All right, so this is what is happening to air gap radial flux density. You can see here peaking at, so these are of concern when you push current, but what is happening to your flux density in the air gap. And then this is the D design, fogging torque, pretty less, 0.06. Back EMF is better here, improved from before in terms of shape. And then your 60 amp base current torque is up to 60 meters, right? So not bad, and less ripple on the torque. So here is your torque versus peak current. Your peak current of 60 amps, the average torque of 5.75 newton meters, light saturation, but normally linear all the way through. So this is your final torque speed curve. You go with the field weakening. So here you can go, basically this is your zero speed. So you are pushing the speed up to, so the 2 newton meter mark, the field weakening, you're pushing it all the way up to almost 3,500, 3,600 RPM. That's the 2 newton mark. So if you see the torque speed curve actually goes like this, right? And we talked about, it's not a flat line. You know, you can continue to extend it where it basically goes like that, right? So that's the nature of the torque speed curve if you continue to push more and more current into it. Okay, so PWM analysis, you can run So this is a tool we use called Motor-solve. Now it is part of Siemens, and you can see if you if you run an inverter with the motor, approximately it can tell you various values in terms of your torque, your various speeds, but the 138 to 8.5 to 12, what your torque is, magnet torque is, reluctance torque is, input power, and output power. Yeah. I think we did that for the design. Okay. So this gives you some kind of flavor. Let me see if there's anything else I want to show you. So maybe I want to also point out some of the analysis we can do in terms of losses. So we have pretty low, let's see here, torque per unit volume, air gap stress, 0.0118 Newton per millimeter square. This is just a figure of merit. Loss is 113 watts loss. So I know now with the 113 watts, I can approximately tell you what my motor temperature is going to be. I don't have to do even thermal analysis. Okay, so the total loss of 113 watts, and if you have this, so go back to thermal analysis, and you have this 90 millimeter diameter and 110 millimeter length, you can say, okay, with 113 watts, what is my temperature rise? And at steady state, you will see that the motor actually stabilizes to that temperature. So that's the beauty of that formula. Okay, so your hysteresis loss is very low, about 3 watts. Your eddy current loss is very low. The back iron loss is very low. The rotor back iron loss is very low. So we are able to achieve 2.7 Newton meter at 4,000 RPM, input power of 1.25 kilowatt, output power of 1.13 kilowatt, efficiency of 90.2%. So efficiency is low. Normally, you're targeting efficiency of 96, 97%. In this case, efficiency is 90.2% at least at this point, where you're pushing 2.7 millimeter at 4,000 RPM. RMS voltage is 27.3 volts, RMS current is 42.4, and you're pushing pretty high current density of 9.4 amps per millimeter square. Power factor is 6.8. All right, so 4,000 RPM gives me those results, and this is the function of your current versus torque. So you can see here 50% rated speed and 100% rated speed, we have a more or less linear relationship between the 50% and 100% speed. This is your input and output power relationship at 50% speed and 100% speed. This is your input power here, and that's your output power. Output power is lower than input power, same here for 100% speed. Okay, this is your estimation of VD and VQ values, 50% and 10%. Right, so you're going to need approximately this purple line here is your VP, peak voltage, up to about 18 volts or so, or 16 volts or so. You have 24 volt DC bus, right? So this is going to be pushing it because 16 volts, we only have half of that voltage available, 12 volts. So you may not be able to push that much current in the motor. And then for 50%, you will need about 7 or 8, 7%. So this is your ID and IQ currents, not voltage currents. right? So here you can see my IQ value here and ID value here. So this is when you do field weakling, that's how it's gonna go negative in the field weakling part. This is your flux linkages. So the flux linkages, if you see here, let's see, yeah, DQ axis. So this is the interesting part, right? So you have green is your LQ, and then this is your LD. Okay, so you have a point of inflection here, right? You have a point of inflection here. Normally, your LQ is always more than your LD value. That's how it starts. But then you have a point of inflection here where this decreases and this increases. And this is because now you're entering into saturation. 30 amps of current, you're actually using any reluctance torque you have, and then you are into pretty heavy saturation. Okay, so this has to be taken into account when you're doing your algorithm design. You have to know this information about your motor if you want to run this motor properly. Flux linkage, this is your Phi-M, which is your magnet flux. And then Phi-D and Phi-Q are your Q and B axis flux. All right, so back into